All right, so that's some practice doing wedge gas diagrams. The next one is, this is diethyl ether, but we're going to skip that one, diethyl ether, which we have two ethyl groups sandwiching an oxygen there. And this one is called acetylene, C2H2. That has a carbon-carbon triple bond. Acetylene. It's linear. This one we'll skip. And then HCN, this one has a carbon-nitrogen triple bond. This would be linear as well, two groups. OCCl2, this is a carbon-oxygen double bond. I can already tell, just looking at this. Chlorine likes to form single bonds. We got two chlorines and then one oxygen. I'm missing one bond. Carbon's got to have four bonds, right? So it's got to double to the oxygen. So we'll go rapidly through some of these other ones here. Did we look at these already?
Yeah.
Okay, let's skip through those. Let's look at the angles here. And so these are going to be angles based on the molecular geometry and the electron pair geometry, not on the Lewis structure. Because the Lewis structures, they have to be accurate. So a lot of times, people will tell me the angle here is 90 degrees. Yeah, and they're right, it is 90 degrees. But I'm asking what would the structure be? Or what would the angle be in the actual molecule? Here, it's not. What is the angle here? 109. What's the angle here? D. 120. A lot of people will say it's 180. And it is 180, but not in the actual molecule. B? So we have bent at 120 or bent at 109? Bent at 109. So 120, let's see. Actually, let's start here. A, it's an angle there. 120 is trigonal planar. B is bent at 109. D is trigonal planar, 120. C is tetrahedral, 109. This molecule is aspirin. Aspirin is a carboxylic acid. You see, it's got the COOH group. What do we call the COOH group? What's the name for that group?
Carboxyl.
It's called the carboxyl group. This group here is what we call an ester. It's a COOC group. A COOC group is an ester. And so this is ester acid. The esters we haven't talked about. That's aspirin. Lactic acid must be an acid, of course. Lactic acid. And we can see, look at it, it has COOH, the carboxyl group right here. So it's carboxylic acid. So let's take a look at the angles. Angle A, tetrahedral, 109. Angle B, well, the EPG is tetrahedral. The MG would be bent at 109. C, trigonal planar angle, 120. So that's a lactic acid.
So with those, we're counting groups, not the individual bonds, right?
For the angles?
Yeah.
The angles are going to be set by the EPG. Yeah, so we count the groups. 1, 2, 3, 4 groups, 109. There's 3 groups, 120.
4 bonds, 3 groups.
Yeah. Oh, yeah, 4 bonds, 3 groups. But we count the groups, not the bonds. The reason is we can't split a double into 2 singles. If we had split a double into 2 singles, then you could. But the double has to be taken together. Same thing with a triple. You can't split a triple into 3 singles. It doesn't work that way. Cinnamaldehyde. The aldehyde group, there are lots of aldehydes like formaldehyde, cinnamaldehyde. Cinnamaldehyde is going to give the flavor, cinnamon, the smell. But if you look at cinnamaldehyde, it has this. This is the COH, but it's a different kind. It's not COH alcohol, it's COH aldehyde. So it's C double bond OH. Then we have some double bonds in here as well. This is kind of interesting because this is flat. You know, benzene, this is benzene ring. It's flat, but this part is flat too because this is trigonal planar, trigonal planar, trigonal planar. So this whole thing's flat. So it's kind of an interesting molecule. What's the angle A? 120. Angle B? And angle C? 120. It's because everything's trigonal planar, including that carbon there. So all the angles are 120. They do here, although it's kind of hard to see, but it's trigonal planar, trigonal planar, trigonal. Everything's trigonal planar, and it's all flat. Now it's flat like this, but you know, across double bonds you can't rotate. They're fixed. This won't rotate. This is rigid. However, single bonds are not rigid, and so this thing can rotate around the single bond, so this whole thing can come out and in. So what we do is just flatten it out on paper to make it easier to write. Single bonds can rotate, so this part can rotate like a propeller. And just flatten it out there. Leave it. Double bonds cannot rotate. Amphetamine. Amphetamine is an example of an amine. Amines will have this ammonia style group here. So nitrogen, hydrogen, carbon. Carbon and hydrogen, you know, they're similar electronegativity, so it's very ammonia-like. So these are called amines. Amphetamine, a lot of drugs are amines. Yeah, like meth. This, if you look at this is the benzene ring here. Do you see that? And then it's attached. Sometimes, you know, you might want to call it like benzyl, like, you know, methane group attached there, methyl. This one is called a phenyl. It's not called a benzyl. And so sometimes they'll call this phenyl. We saw this with methylphenyl ether. I don't know if you remember that one. But there's a methyl group on one side and a phenyl group on the other. So we had methylphenyl ether. Let me see. Maybe I'll bring that one back up because that was in chapter 12. No, sorry. It was in chapter. What chapter was that? 13. So here's diethyl ether. We have two ethyl groups here, sandwiching the oxygen. The tetrahedral, band, tetrahedral. Here, this is another ether, but on one side we have a methyl group, a CH3 group, and on the other side we have a benzene ring. So it's just missing a hydrogen. We take the hydrogen off, attach it to the oxygen. When benzene acts as what we call a substituent, attaches to something else, then we call it phenyl. So this is called methylphenyl ether. Methylphenyl ether. This is just another name for benzene ring. Benzene rings are quite common. You know, the benzene itself is a common constituent in gasoline, although not in high concentrations. Benzene is a very popular solvent. Anyway, so we have this kind of benzene-like ring here, and then let's see. So what's the angle A? Did we already do the angles here? No. 120. Angle B. Tetrahedral. So therefore the angle is 109. So you can see, you know, this you can see the leg, one foot forward, 1 foot back, and both arms out like this. So this tetrahedral totally looks different than this. So a lot of people, they can't make the distinction when they try to do a 3D drawing, they try to model it after this. No, you gotta throw this out and just model it off the tetrahedral. Here. Now, what is the geometry on nitrogen here? The molecular geometry. I know the electron pair geometry. What is the EPG on nitrogen? Tetrahedral. So the angle must be 109. It's trigonal, the pyramidal. And so this is trigonal pyramidal. The lone pair is sticking into the board. And therefore, we're seeing the bottom of the pyramid. This is the base of the pyramid here. And the lone pair is going straight out. You know, again, with this bond, we can rotate it. And so I would have rotated this and had the lone pair sticking straight up so I could see the pyramid from the side. You know? So that particular amine group I would have drawn like this. You know, as it, they have it coming up. I would have the nitrogen here, the lone pair sticking straight up, and therefore I'd have one hydrogen coming out, one hydrogen going in. This is bond with carbon here. Drawn it like that. Rather than like how they have it there. And that's perfectly fine because I can rotate it. You know, this whole thing, in fact, this whole thing's flopping around because the single bonds are rotating. This is not flopping around. It's got double bonds. This is pretty rigid. But from here, we can flop around. So what we got to do is freeze it and then draw it. When we freeze it, we try to press it down into the page so it's as flat as possible and then draw it, you know. Makes it easier to draw that way. So that's amphetamine. Next, we have a series of multiple choice questions, but we're going to answer all these at once. Is this polar or non-polar? All these bonds are polar. And so we look at A. Is that a polar molecule? Do the bond dipoles, remember we call them bond dipoles, do the bond dipoles cancel or not cancel? And so is A polar or non-polar? A is polar. If you don't like that way of trying to visualize if they cancel, you know, like that, then your book has a very simple rule. Your book says if there's a lone pair, it's going to be polar. And so there's lone pairs, it's polar. B, non-polar. B is going to be non-polar because it doesn't matter, you know, which way the bond dipoles point. That molecule is what? Shape. Linear. So if it's pulling out to A, they're equal and opposite. You know, this is pulling this way, this is pulling this way, it's going to go nowhere. Or if it's pulling into B, then it's still going to go nowhere. You know? And so the bond dipoles are equal and opposite no matter which way they point, therefore they cancel each other out. If the bond dipoles cancel each other out, then the molecule is non-polar. Or as your book would say, there are no lone pairs, therefore it's non-polar. But I don't think that rule holds all the time. It's okay, we'll use it. How about this one? Lone pair, it's going to be polar. This one, non-polar. The other way of thinking about it is looking at the bond dipoles. Here we have a three-way tug-of-war. In this three-way tug-of-war, there's going to be no winner. You know, one A is not stronger than the other. And so if they're pulling in these directions, then there's going to be no net movement. How about this one? Non-polar. But it's not because they're pulling at 90, they're pulling at what angles? 109. So it's like being inside the sphere, you know, one leg forward, one leg back, kind of thing. Arms up. Is the carbon tetrachloride molecule CCl4, which contains 4 polar bonds, carbon-chlorine bonds have an electronegativity difference of 0.5. Polar or non-polar? The bonds are polar, however, the molecules will be non-polar. Does everybody see that? It's because of the tetrahedral symmetry. Okay, let's imagine a two-way tug-of-war. A two-way tug of war, you can see both A's are equal in strength. This is going nowhere, right? And then we do a three-way tug of war. If all three A's are equal in strength, is this going anywhere? That's not going anywhere. Now let's do a four-way tug of war. A four-way tug of war I'm going to draw like this. Okay, if I look at these two A's, they're going to be pulling this direction, right? However, I have two other A's pulling the opposite. It doesn't look like it's the opposite, but it is the opposite. These two A's are going to pull this way. These two A's are going to pull the opposite direction with equal strength. And so the bond dipoles end up canceling each other out. The other way of visualizing this is what we call spherical symmetry. And spherical symmetry, we position these A's evenly around the surface of the sphere. You know, and since they're evenly distributed around the surface of the sphere, they're going to cancel each other out. There's a tetrahedral. It's going to be non-polar. Non-polar. It says CCl4 molecules are nonpolar because the polar bonds are symmetrically arranged, which makes the molecule itself nonpolar because when they're symmetrically arranged like that, they cancel each other out. BF3 is trigonal planar, that's going to cancel each other out. NH3 is trigonal pyramidal, that doesn't cancel each other out. GH4 is tetrahedral, that will cancel it. And so BF3 nonpolar, NH3 is polar, being trigonal pyramidal, and GH4 being tetrahedral is nonpolar. Describe the shapes and compare the polarities of HF and HBr. Well, whenever we have two atoms, the shape is easy. Two atoms are always going to be linear regardless of the EPG. It doesn't matter what the EPG is. Two atom molecules are going to be linear. Which one's more polar, HF or HBr? HF is more polar because fluorine is more electronegative. And so more polar just means that it's going to have a bigger separation of charge, which means H is going to be more positive. The HN is more positive. And so both molecules are linear, even though EPG is tetrahedral on both fluorine and bromine. For each formula below, draw the Lewis diagram and determine the polarity. You know, like something like BEF2. BEF2 is what? I'm not going to draw the little pairs here just to save time. BEF2 is linear, therefore it's going to be nonpolar. H2O it has lone pairs, which is going to screw up. It's linear. It's going to be bent now. It's going to be polar. BF3 is nonpolar. Sketch the Lewis diagram of the water molecule, paying particular attention to the bond angle and using arrows to indicate the polarity of each bond. Then sketch the methanol molecule, again using arrows to show bond polarity. Predict the approximate shape of both molecules around the oxygen atom. Also predict relative polarities of the two molecules and explain your prediction. So let's talk about this one next. And so I'm going to draw H2O. When I look at H2O, what is the EPG? Tetrahedral. And so I'm going to have two in the plane, one coming out, one going in. And so for water, what I'd like to do is I'd like to put the two bonds in the plane. So let's go ahead and put the two bonds. That means one lone pair sticks out of the plane, and then one lone pair sticks in. Okay, so this would be my tetrahedral EPG, which results in a bent MG here. All right, for methanol, what we're going to do is we're going to start off with the oxygen end here. And so in methanol, let's draw the Lewis structure here. I'm going to draw it backwards like water. It's just like water, HO, except rather than HOH, it's HOC. And then it's not a C, it's going to be a CH3. And so I'm going to put the two bonds in the plane like this. And so we'll put an H here and a C here. And one lone pair comes out. This one lone pair goes in. Okay, now the C, what does the C have next to it? 3 H's. But let me stop here just for a moment. What's the electronegativity difference between H and C? Are they close or are they kind of far apart, the electronegativities? Carbon and hydrogen have very close electronegativities or very different electronegativities? Different? How many people think different? Well, it's probably best if you know the numbers, but you shouldn't need to see the numbers because you should know something about hydrocarbons. Are hydrocarbons polar or nonpolar? Hydrocarbons are nonpolar regardless of the shape. And the reason is because the carbon-hydrogen bond is nonpolar because the electronegativity difference is so small. Since the electronegativity difference is so small, that means they're close in electronegativity. Now, what do I mean by so small? You might not think it's so small. It may not seem so consistent the way people talk about these, but let's take a look at the electronegativities here. Okay, do you see? Carbon is a 2.6, hydrogen is a 2.2, so electronegativity difference is 0.4. And you think, oh, 0.4 seems significant, but in the scheme of things for this, 0.4 is not significant. And so that means that when I draw the bond dipoles, I can draw them about the same side. Which one's more electronegative, oxygen or hydrogen? Oxygen. So I'm going to draw a bond dipole like this, and one like this. Now, are these equal and opposite? No, they don't cancel each other out. And so what we're going to end up with is a net molecular dipole. Which direction is this going to go? If oxygen's pulling on this one and oxygen is pulling on this one, which direction will the oxygen go? Yeah, it's going to go bottom left. And so the net molecular dipole, this would be the molecular, it's going to be a polar molecule because these two bond dipoles add up to a net molecular dipole of this. Now, I'm going to have a bond dipole here exactly the same. This one is going to be very close, but not exactly. It's just going to be a little bit weaker because oxygen is going to have a little bit harder time pulling out carbon, but not much. Because carbon and hydrogen are about the same. And therefore, when I look at the polarities are about the same thing. Polarities are about the same. And so when I think about methanol and I think about water, I think, oh, they're very similar. They're very similar. In fact, this leads to one property, a physical property called solubility. Solubility is how much you can mix together. And so let's say I have a bucket of water. You know, is there any limit to how much water I can pour into a bucket of water? Is there any, well, until it overflows, but okay, let's say in the ocean, is there any limit to how much water I can pour into the ocean? No, I mean, it's just going to mix. How about if I try to pour oil into the ocean? Are they going to mix? No, because they don't like each other. Water likes water, so water is going to mix with water, right? Now, methanol is very water-like, and so methanol will be warmly welcomed by water. And so if I were sitting on the ocean, is there any limit to how much methanol I can pour into the ocean? No, because it's like pouring water into water. That's what it's like. And so methanol is what we call miscible in water. You can mix it in all proportions. And the same thing, if I have a pool of methanol, I can add as much water to the methanol as I want because they mix, they like each other, they mix. But then you look at this part. This part is not polar. This part is non-polar, but fortunately it's not so big, you know. And so methanol, what we're going to have is we're going to have a methyl group here. There's another name for methanol. Another name for methanol is methyl alcohol. This is a methyl group here. This is the alcohol. The methyl group, however, is non-polar. The methyl group doesn't really like water because it's non-polar. Methyl group likes oils more. But it turns out it's not so big, and therefore methanol still mixes. In fact, we can make this bigger. What's bigger than a methyl group? An ethyl group. An ethyl group would have one more carbon. And so ethyl alcohol is also miscible in water. We can mix ethanol and water in any proportion we want. What's bigger than ethyl? Prop. You know, prop is 3 carbons. Propanol. Propanol is pretty soluble in water. However, when we get to butanol, how many carbons does butanol have? 4 carbons. Butanol is insoluble in water. Butanol, if you try to pour butanol into water, they don't mix. Why? Because this non-polar hydrocarbon part dominates then the polar water-like part. So methyl alcohol, no problem. Ethyl alcohol, no problem. Propyl alcohol, probably okay. Butyl alcohol or butanol, forget it. It's not going to happen. Pentanol, no, it's not going to happen either. It's going to be more oil-like than water-like. All right, let's look at the shapes. What's the shape of the oxygen here? When they're asking the shape, they're asking molecular geometry. What's the molecular geometry around oxygen? Bent. Because we don't see. Can you see the electron cloud when you look at this? No. You see it as Heisenberg uncertainty. Here, what's the shape on this? Bent. It's the same shape. Except we have this one. We have one additional central atom. You know? Here we have the 1 central and 2 terminal. We have to do this central atom by central atom. So first we look at oxygen. What's bent? 109. Then we go to the carbon. What's the shape around carbon? Tetrahedral. Angle? 109. So Mg is tetrahedral, Mg is bent. So they're just drawing bond dipoles directly there. I drew them off to the side. This is kind of funny because Lewis structures, did Lewis structures accurately portray the shape? No, not at all, because if you look at this, these look equal and opposite, don't they? And so it looks like they cancel here, the 2 bond dipoles, but they don't because this is bent. In fact, these 2 have the same exact shape. They just drew them differently. That's it. So these you'd actually have to draw, you know. Like SiCl4 is tetrahedral, no lone pairs. If it's tetrahedral, no lone pairs, then it's going to be polar or non-polar. Non-polar. SeH2 has lone pair and it's bent. Therefore, this should be polar. And this is an interesting one because, you know, you look at it and carbon likes to form how many bonds? 4. So there's got to be a double bond, otherwise we just don't have enough. And so something like that we can just draw easily. It's going to be this. Do you know what this molecule is called? This one's called formaldehyde. Formaldehyde. Anyway, this one's polar. It's polar. Even though there are no lone pairs. Well, there are no lone pairs are supposed to be polar according to them. Which species? Okay, well, let's just go through the shapes here. What's the shape of this? BH4 minus. There's a negative formal charge on boron. Tetrahedral. If it's tetrahedral, is that polar or non-polar? It's non-polar. It's non-polar meaning that this is a very symmetric molecule. However, it's an ion. And so normally when we think of a pole or molecule, we think of a dipole. There's a positive end and a negative end, a dipole. This is actually a monopole because this is a negative ion. So it's a monopole. All ions are going to be monopoles. They're just going to be negative monopoles. Yeah. Although, you know, any bond dipoles in here would cancel. How about PCl3? That's going to be polar. And the shape? Not tetrahedral. When I say the shape, I'm talking about the Mg. The EPG is tetrahedral. That's correct. But the Mg is trigonal pyramidal. It's not going to cancel. How about this one? This one, again, the EPG is tetrahedral, but the shape is not linear. It's bent. This is like water. Yeah, because of the two lone pairs. It's like water. This is going to be bent at 109. It should be. Although in Chem 1A you'll learn.
Doesn't formaldehyde have like one more hydrogen than drinking alcohol or something?
Formaldehyde than drinking alcohol? You don't want to drink this one. But when you metabolize alcohol, it undergoes a series of steps, a series of oxidations. And so, do you remember when I said the alcohol in the wine turned into vinegar? It didn't go straight to vinegar. What probably happened was this. The alcohol, which is ethyl alcohol or ethanol, probably went to ethanal. Ethanal is CH3CHO, which is an aldehyde. And then it went to ethanoic acid or acetic acid, CH3COOH. And so it underwent partial oxidation from ethanol to ethanal, from ethanal to acetic acid. And then it can continue. In the body, that happened in the bottle. In the body, when we look at ethanol, metabolism, it doesn't happen in one step, it's not like one step that's metabolized. What happens is these aldehydes are these aldehydes are not friendly. If you've ever smelled formaldehyde, it smells awful, right? Yeah. And you don't want, if you drink ethanol, you don't want your body filled up with aldehyde. And you don't want your body filled up with acetic acid like vinegar. You want to metabolize that stuff quickly. So some people say, and because I don't know all the mechanisms of hangovers, but some people say hangovers from all the aldehyde that's, incomplete oxidation of ethanol. Your body is doing the same thing. Too much aldehyde, too much acetic acid or whatever, maybe. And so if we look at this, what happened to it? We just wanted this diagram here. The first step in ethanol metabolism is it gets oxidized. It goes from ethanol and it's partially oxidized to acetaldehyde or ethanal, called ethanol. And so this is aldehyde gives us toxic hangovers. Aldehydes, and they smell nasty. And then it goes from here to acetate, which is essentially acetic acid. It's acetate in base, or acetic acid in acid solution. So this must be, pH must be a little high if it's basic, so it's acetate. And so what happened in my wine was that my ethanol got oxidized to this point. But I'd rather drink acetic acid than acetaldehyde. Actually, I'd rather not drink either, though, if I had to drink one. And then it gets thrown into your regular metabolic cycle. The acetyl-CoA goes into your regular metabolism. Yeah. And so ethanol has calories, So this is the beer belly type thing, where you get a lot of calories from drinking alcohol. So, but structurally, it's kind of different, you know. It's different. Structurally, in fact, what we can do is, since we're on Lewis structures, let's just take a quick look at the oxidation states. You know, this metabolism is redox chemistry. So if we look at ethanol, what's the oxidation state on this carbon? Well, I know the formal charge is 0, but what is the oxidation state on that carbon? What is the oxidation state on this carbon? How many ways did I give you to determine oxidation states? Three. So this is the method using, the advantage of this is, you know, if we use the standard Chem 4 method for determining oxidation states, what we get is the average. So if I were to do ethanol like this, ethanol is typically written C2H5OH. And so what we do here is we do the hydrogens first. The hydrogens go at +1. And so these hydrogens are +1, so that gives me a total of +6. And the oxygen is -2. So +6 minus 2 is +4. That means I need a -4, so each carbon must be -2. So -2 times 2 gives us -4, and then it adds all up. Well, the problem with doing oxidation states with this method is this is the average oxidation state on the carbon. I don't want the average. I want the individual oxidation state on the carbon atom. What is the individual oxidation state? We can do using Lewis structures quite easily. Did anybody review that? I should have asked that on the last test. That would have been the easy question to grade. Everybody would have. How many ways are there counting electrons in Lewis structures? There's the octet, there's formal charge, and there's oxidation state. Only difference is how we divide the electrons. So. Okay, let's take a look. This one is you're right, -1 and -3. How did you figure that out?
I just canceled it in my head. I just went to hydrogen +1 with oxygen, so it cancels out one of the minuses from oxygen. So it's only -1 there. Then you have hydrogen above, the hydrogen above and under it, that's +2. And then I canceled that out with the negative left over from the oxygen, giving me +1. So to balance it out, I need -1.
That sounds very complicated.
Yeah.
I do it like this: winner take all. Winner take all. And so oxygen takes all. Does carbon versus hydrogen? Carbon wins. Carbon versus carbon? Well, winner can't take all. Carbon versus carbon's a tie. So it ends up with 1, 2, 3, 4, 5 electrons. It's supposed to have 4, it's -1. Here, winner take all. Carbon versus hydrogen, carbon wins. Carbon versus carbon, it's got to be a tie. So 1, 2, 3, 4, 5, 6, 7. 7 electrons is -3. That's how I earned it. Oxygen, I'm going to take all of them. So it's -2. Hydrogen gets none. All the hydrogens are +1. Let's go to ethanol. Okay, this gets converted into ethanol or acetaldehyde. Oh, what's the oxidation state of this carbon here?
Plus one. Oh, wait, no, zero. Yeah, zero.
That carbon. Okay, let's just do tug of war here. Carbon versus hydrogen, who wins? Carbon, so it takes both. It's two electrons. Carbon versus hydrogen, who wins? Carbon, that's 4 electrons. Carbon versus hydrogen, who wins? That's 6 electrons. Carbon versus carbon, who wins? It's a tie, 7 electrons, 1 each. So 7 electrons, it's supposed to have 4. Therefore, it's -3. You do the same thing. You got to practice this. If it doesn't make sense during lecture, ask me. During class or at least before the test. Make sure it makes sense. In case, just think if I put a 20-point question asking you to determine the oxidation states on the Lewis structure, that would have been 20 lost points. That happens. That happens because it's hard to predict what's going to be asked sometimes. There aren't a lot of questions. Okay, here, carbon versus oxygen, who wins? Oxygen, so carbon lost all of those. Carbon versus hydrogen, who wins? Carbon, so that's 2. And so we got 1, 2, 3. It's supposed to have 4, therefore it's going to be +1. Oxygen doesn't change, oxygen is still -8. And hydrogens are all +1. So only thing that changed, who lost? The only thing that changed is this carbon went from -1 to +1, so it was oxidized. It was partially oxidized. Carbon can go all the way to +4. So it was partially oxidized. What did the oxidation? Well, let me tell you what did the oxidation. You know what did the oxidation? An oxidizer. What was the oxidizer? The name of the oxidizer. The name of the oxidizer? Actually, we don't need to know. These are kind of hard to read. This is called an enzyme, alcohol dehydrogenase. And then this is the other half of the redox reaction. It's called NAD. NAD plus, NADH. One of these is an oxidizer, the other is a reducer.
It's based on electronegativity.
Yeah. Based on electronegativity. Okay, obviously I went over time here, so let's take a break and then we'll start up again. That break.